People always want to know the answers to big questions. Where did we come from? How did the universe begin? What does it mean? Is there something else somewhere? The stories of old times no longer seem as true or relevant. They have been replaced by various beliefs or superstitions. But real science is sometimes more surprising and satisfying than science fiction. I myself am a scientist and have a great interest in physics, cosmology, the universe, and the future of humanity. My parents always encouraged me to ask questions and learn. Like my father, I have always tried to find answers to these questions. I have spent my entire life mentally exploring the universe. Through theoretical physics, I have tried to find answers to many big questions. At one time, I thought I would see the end of physics, but now I feel that the journey of discovery will continue even after me. We are close to finding answers to some questions, but we have not yet found them. The problem is that most people believe that real science is very difficult and incomprehensible, but I don't believe that. Those who want to do research really need to dedicate a lot of time. And if everyone started doing only theoretical physics, the world would stop. But today, everyone can understand the basic ideas if someone explains them in simple language, without formulas. And that's what I've always strived for in my life. This has been a great time to research theoretical physics. Our understanding of the universe has changed significantly in the last 50 years. I'm glad I've contributed a little to it. The greatest thing about the space age was that we got a chance to see ourselves from a common perspective. All of humanity is one. There's one planet, one race. I want to be among those who demand action on the world's major issues. I hope that in the future, even when I'm gone, those who have the power will show courage, wisdom, and leadership. They will work for everyone, not just themselves. Time is precious. Seize the moment. Do something right now. I've written about my life before, but some things keep coming back to me when I think about my pursuit of big questions. I was born on the same day that marked the 300th anniversary of Galileo's death. I think this influenced my scientific life. In fact, about 200,000 other children must have been born on that day, but I don't know if any of them were interested in astronomy. I grew up in an old house in Highgate, London. My father had bought it cheaply during World War II. One day, a V-2 rocket landed near our house. But at the time, I was out with my mother and sister, and my father was fine. After the explosion, there was a large empty plot for many years where I used to play with my friend Howard. With that same curiosity, that same inquisitiveness, I tried to understand everything. In 1950, when my father's job shifted, we moved to St. Albans. I started at the high school for girls, which admitted boys until year 10. Later, I joined St. Albans School. I always remained in the middle of the class, but my friends called me Einstein. Perhaps they saw something special in me. At age 12, one friend told another that I wouldn't amount to anything. I had 6 or 7 good friends at St. Albans, and we would debate everything, especially the beginning of the universe and the need for God. I remember hearing that light from distant galaxies is redshifted, which gives an idea of the universe's expansion. But I thought there might be some other reason, or perhaps the light gets tired along the way. A uniform, unchanging universe seemed more natural. Later during my PhD, when the cosmic microwave background was discovered, I realized I was wrong. I always wanted to know how things worked, so I would dissect things, but I couldn't put them back together. My father always encouraged me to pursue science and wanted me to go to Oxford or Cambridge. Having attended Oxford himself, he wanted me to apply there too. At that time, there were no fellows for mathematics at University College. So I tried natural sciences and surprisingly I got a scholarship. Oxford had a very laid-back atmosphere. You had to appear brilliant without effort or give up and get a 4th-class degree. I studied very little accordingly, but when I got sick, my thinking changed. When you feel like life could end quickly, you feel like you have a lot to do. Because I had studied less, I thought I would only take questions in the exam that didn't require memorizing facts and choose theoretical physics. But on the first day of the exam, I couldn't sleep and didn't do well. My result was between 1st and 2nd class, so I was called for an interview. There I was asked what I wanted to do next. I said, if I get a 1st, I'll go to Cambridge. If I get a 2nd, I'll stay at Oxford. They gave me a 1st. After the final exams, the college offered travel grants. I thought the further I went, the better my chances would be. So I talked about going to Iran. In 1962, I took a train to Istanbul, then to several cities in Turkey and Iran. On the way back, my friends and I had to stay in Iran during a major earthquake. I suffered a fever and a rib injury from the jolt of the bus. We didn't know what had happened for several days because we didn't know Persian. We found out when we arrived in Istanbul, and I sent a card home. Despite the earthquake, I have fond memories of the trip to Iran. I felt that this was the only time my curiosity had risked my life. I was 20 years old when I went to Cambridge and enrolled in applied maths and theoretical physics. I applied to work with Britain's greatest astronomer, Fred Hoyle, but didn't get a place. I met Dennis Sciama, whom I hadn't even heard of. It was a good thing because defending Hoyle's stiff state theory would have been a very difficult task. I started by reading old textbooks and, as always, gravitated towards the biggest questions. In my third year at Oxford, I noticed I had become a bit clumsy. I fell 2 or 3 times and couldn't steer the boat properly. Later, a doctor told me to stop drinking beer. But the real problem was something else. After arriving at Cambridge during a cold winter at home, my mother encouraged me to go skating, and I fell. My mother sensed something was wrong and took me to a doctor. Weeks of tests were conducted at a London hospital. In 1962, tests weren't as advanced as they are today. Muscle samples were taken, electrodes were inserted, and medication was injected into the spine. The doctor never explained exactly what the problem was. But from his words, I understood that this disease could not be cured. Eventually, even the doctor gave up. Somewhere along the line, I realized it was a disease, amyotrophic lateral sclerosis, in which the nerves in the brain and spinal cord gradually lose their function. A person gradually loses the ability to walk, speak, eat, and even breathe. My illness initially progressed rapidly. I became depressed and felt there was no point in completing my PhD because I didn't know how long I would live. But then the disease slowed down a bit and I started looking at life in a new way. When hope fades, every day feels like a bonus. As long as there's life, there's hope. And yes, there was a girl in my life, Jane. She was very positive that we could fight my illness together. Her courage gave me strength too. After our engagement, I realized that if I wanted to get married, I would have to work and complete my PhD. As always, big questions kept me motivated. I worked hard and enjoyed it. During my studies, I applied for a research fellowship at Gonville and Council College and received it. This was a turning point in my life. It allowed me to continue my research despite my worsening illness. Jane and I got married. We had 3 children, Robert, Lucy, and Timo. As a father, I always taught my children to keep asking questions. My son, Tim, once told me in an interview that he asked me if there could be smaller universes surrounding the universe. I told him never to be afraid to ask an idea or a question, no matter how strange it might seem. Around the 1960s, the biggest question in cosmology was whether the universe had a beginning. Many scientists were opposed to this idea because they believed that if there was a point of creation, science would end there, and then one would have to rely on God or religion for answers. This was the question I needed to address in my PhD thesis. Roger Penrose had shown that when a star dies and becomes very small, a singularity eventually forms where space and time end. I thought the same thing might apply to the expansion of the universe. This meant that space-time begins at some point. In 1970, a few days after the birth of my daughter Lucy, I had a big idea. I thought the same theory I had formulated for singularities could apply to black holes. If general relativity is true and the energy density is positive, then the event horizon of a black hole, that is, its boundary area, will always expand when something falls into it. If 2 black holes collide to form one, the event horizon of the new black hole will be larger than the total area of both the old black holes. This period was a golden age for black hole theory. We had solved major problems, even though there was no concrete evidence for black holes. My and Pence's research showed that general relativity doesn't work at singularities. The next step was to combine general relativity, which is for very large objects, with quantum theory, which is for very small objects. I thought it was possible that there might be a small black hole in the nucleus of an atom. I saw a deep connection between gravity and thermodynamics. And I solved an old question. If a black hole is shrinking and disappearing, where does the information in it go? I discovered that information goes out but doesn't return like work. Just like when you burn a book, only smoke and ashes remain. To understand this, I observed what would happen if a quantum particle fell into a black hole. I thought a small portion would go into the black hole, and the rest would scatter out. But to my surprise, I saw something coming out of the black hole. This was exactly what was needed. To connect the area of a black hole's event horizon with its entropy, the uncontrollable state of the system. This entropy is a function of the area of a black hole's event horizon and 3 constants of nature: the speed of light, or c, is related to Newton's gravitational constant, or capital G, and Planck's constant. The thermal radiation emitted by black holes is now called Hawking radiation, and I am proud of this discovery. In 1974, I was made a Fellow of the Royal Society. I was young and only a research assistant, so everyone in the department was surprised. But 3 years later, I became a professor. My research on black holes gave me hope that one day we would create a theory of everything, and this pursuit kept me going. That same year, my friend Kip Thor invited me and my family to California. I used a manual wheelchair and a blue electric three-wheeler. In California, I used an electric wheelchair full-time for the first time, which gave me considerable independence because the buildings and paths in America were more accessible to disabled people. When I returned to Britain in 1975, the environment there seemed a bit limited and boring compared to America. But my mood improved again. When I was successful, and in 1979 I was awarded the Lucasian Professorship, a position once held by Isaac Newton and Paul Dirac. In the 1970s, I was working on black holes. But then my interest returned to the universe when I discovered that the universe was initially expanding very rapidly. This is called inflationary expansion. I also worked with Jim Hole on the no-boundary theory, which proposed a new way of explaining the beginning of the universe. By the 1980s, my health deteriorated further. I even had difficulty eating. In 1985, while visiting Saran, Switzerland, I developed pneumonia. I was put on a ventilator in the hospital. The doctors told my wife Jan that nothing could be done and suggested turning it off. But Jan refused, and I was brought back to Cambridge by air ambulance. It was a very difficult time, but the doctors at Cambridge tried very hard. My laryngeal muscles were weak, allowing food and saliva to enter my lungs. Therefore, I had to have a tracheostomy. This caused a loss of voice. Previously, my speech was so unclear that only my family could understand it. After the tracheostomy, I could now spell words from a card by moving my eyebrows. Then, a computer expert in California, Wyatt Voltis, sent me a computer program called Equalizer, which allowed me to select words on a screen. Now I use a program called ACAT, which is activated by a sensor in my glasses, triggered by my cheek movements. It also has a mobile phone, allowing me to access the internet. Today I can call myself the most connected person in the world. I kept my original speech synthesizer because it had a distinctive voice, even though it had an American accent. In 1982, I had the idea to write a popular book on the universe. I thought it would generate some money for my children's education and my care. But my real goal was to show the world how far our understanding of the universe had come. It's important that we ask questions and seek answers. And as a scientist, I wanted to share what I was learning with everyone. A Brief History of Time was first published in 1988 on April Fool's Day. It was originally titled From the Big Bang to Black Holes, A Short History of Time, but the title was later shortened. I never imagined the book would become as popular as it was. Perhaps my struggles and disabilities were a factor. Maybe not everyone read the book completely or understood everything, but it certainly helped people understand that we live in a universe that can be understood. To my colleagues, I'm just a physicist, but to the general public, I became perhaps the most recognizable scientist. Because scientists, with the exception of Einstein, aren't usually famous, and perhaps my disability also contributed to this. Being in a wheelchair meant I couldn't hide. Being popular has its advantages and disadvantages, and the advantages outweigh the benefits. People are happy to see me. I had a huge audience at the London Paralympic Games in 2012. I've lived a truly unique life in this world. I've explored the universe through extraordinary life and my mind. I've contemplated the ends of the galaxy, entered a black hole, and reached the beginning of time. I've experienced life's ups and downs, difficulties, success, and hardship. Sometimes I've been rich, sometimes poor, sometimes healthy, sometimes sick. I've received praise and criticism, but I've never been ignored. I'm very happy to have contributed to understanding the universe. But without my loved ones in my life, it would all be incomplete. Ultimately, the most important thing is that we humans, ourselves made up of tiny particles of nature, have succeeded in understanding the laws of the universe. This is a huge achievement. I want to share my excitement about these questions and discoveries with everyone. I wanted to become a great scientist. But in school, I wasn't a very good student, always in the middle of class. My work wasn't very neat and my handwriting was poor. But I had good friends, and we would talk about everything, especially the beginning of the universe. That's where my dream began, and luckily, it came true. Chapter 1. Is there a God? Science is now answering questions that were previously answered by religion. In ancient times, people thought God created everything because the world was so scary and natural phenomena were difficult to understand. Today, science has a better answer, it is. But people still cling to religion because it gives them solace, and they don't trust or understand science. A few years ago, a newspaper published an article that Hawking said, "God didn't create the universe." They featured a photo of me and God facing each other, as if they were in a competition. But I'm not angry with God. My job isn't to prove whether God exists or not. I simply want to understand how the universe works. People used to believe that people with disabilities were cursed by God. But I believe that everything can be explained by the laws of nature. If you believe in science, you believe that certain rules always apply. Even if someone calls them God's work, that's just a definition, not proof. In ancient times, a philosopher named Aristarchus considered lunar eclipses not to be caused by God, but rather the Earth's shadow. He understood how the sun, earth, and moon are interconnected. He even theorized that the Earth isn't the center of the universe but revolves around the sun. He explained that stars are like the sun, just much farther away. In this way, the universe is a machine that operates according to rules that humans can understand. I believe that discovering these laws of nature is humanity's greatest achievement. These rules tell us whether we need God to explain the universe. These rules explain how things work in the past, present, and future. These rules apply everywhere, not just to the flight of a ball, but to the entire universe. Human-made laws can be broken, but not the laws of nature. This is why they are so powerful, and sometimes even conflict with religion. If you believe that the laws of nature are fixed, then what role does God play? This is the biggest difference between science and religion. Some people say that God is just another name for those rules. But most people think of God as a human being with whom they can form a relationship. When you look at the vastness of the universe and think about how small and accidental humans are in it, so that idea of God doesn't seem true. I give the word God the same meaning as Einstein did, the laws of nature. I believe we will one day fully understand these rules, and this is the mind of God. Now, the only area left for religion is the beginning of the universe. But even here, science will soon find the answer. How did the universe begin? I wrote a book, Did God Create the Universe? And people were outraged that a scientist shouldn't ask such a question. But for me, this question is also a scientific one. Who created the universe? There is no bigger question than this. I believe the universe came into being from nothing, according to the rules of science. The basic principle of science is scientific determinism. Its rules determine how the universe will change. Whether God created these rules or not, he can't change them now. Otherwise, they wouldn't be called rules. If God wishes, he can only determine the beginning. But perhaps there are rules there too. That means God has no freedom left. No matter how vast and strange the universe is, it requires only three things. It's like a cookbook. The first is matter, what we see all around us. Land, rocks, gas, and everything. The second is energy, like the sun's heat and light. The third is space, meaning vast empty spaces. The universe is simply space. Then the question arose, where did all this matter, energy, and space come from? The answer was that Einstein explained that matter and energy are two forms of the same thing. The famous formula E number mc2 states that matter and energy can be interchanged. This means that the universe only needs energy and space. All of this was created instantly at the time of the Big Bang. At the time of the Big Bang, the entire universe and space were created simultaneously. And there can be no creator. People want answers. Why are we here? When someone asks me, did God create the universe? I say the question itself is wrong. Since there was no time before the Big Bang, God didn't have time to create the universe. For example, if someone asks, where is the edge of the earth? The earth is round, a sphere, and has no edge. If God exists, and I get the chance to meet him, I would ask, how did you conceive of such a complex thing as M-theory in 11 dimensions? But my belief is that the universe is made up of the rules of science, and that is the best answer. In Chapter 2, How Did It All Begin? Shakespeare's character Hamlet said, I can consider myself king of infinite space. Even if I am confined within a tiny nutshell, this means that humans, though limited by their bodies, can contemplate the entire universe through their minds. That too, to a point where even the Star Trek didn't reach. The question is the universe truly infinite? Is it truly infinite or just very large? Did it have a beginning? Will it last forever or just last a long time? Can our small minds comprehend such a vast universe? I think we should try to understand the universe. Early people also asked these questions. Why are we here? Where did we come from? For example, the Boshingo people of Africa believed that in the beginning there was only dark water and the god Boomba. Boomba had a stomachache. He spat out the sun, which dried up some of the water and formed land. Then he created the moon, stars, animals, and finally, humans. Such stories try to explain where humans came from. In ancient times, people believed humans had arrived recently because their knowledge and technology were rapidly advancing. But the mountains and rivers remained the same. So it seemed they either existed forever or were created alongside humans. Not everyone was willing to accept that the universe had a beginning. People like Aristotle believed that the universe has always existed because what exists forever appears more perfect. They argued that the progress we see is due to repeated floods or disasters, which restart everything. For those who believed the universe had a beginning, this was proof of God's existence, such as the prime mover. If we assume the universe had a beginning, the question arises, what existed before the beginning? What was God doing? Was he planning hell for those who ask such questions? The German philosopher Immanuel Kant pondered this deeply. He wondered, if the universe had a beginning, why didn't anything happen before for infinite time? And if the universe always existed, why did it take infinite time to reach its current state? Both seem confusing. They all believe that time has been moving forever, whether the universe exists or not. Even today, many scientists think this way. But in 1915, Einstein proposed his general theory of relativity, which states that space and time are not fixed, but rather they change with the universe's matter and energy. This means that thinking about time before the universe's beginning is pointless. Like trying to travel further south from the South Pole. Einstein's theory linked space and time, but it didn't explain much about space itself. Space appears to be endless. New instruments like the Hercules telescope reveal that there are billions of galaxies. Each galaxy contains billions of stars, and they likely contain planets. We often think space moves forever and is almost the same everywhere. Although space appears the same, the universe changes with time. People previously thought the universe remained the same. But if the stars had always been burning, the night sky would be as bright as day. But the darkness at night means the universe wasn't always like this. Stars burned somewhere some time ago, so their light hasn't reached everywhere yet. In the 1920s, Edwin Hubble, using the Mount Wilson telescope, discovered that many faint spots of light were actually galaxies, meaning very distant stars. Their light takes millions of years to reach us. So the universe couldn't have begun thousands of years ago. Hubble's second major discovery was that other galaxies are moving away from us. And the faster the distance, the faster. This means the universe is expanding. This suggests that everything was once close together. Perhaps 10 to 15 billion years ago, everything was in the same place. But many scientists were unhappy with the universe having a beginning because it seemed to imply that the laws of physics were failing somewhere, requiring something like God. So they proposed theories that the universe is expanding but never began. One was the steady-state theory, which posits that as galaxies move apart, new matter in the intervening space creates new galaxies. This theory was tested. When the sky was observed using radio waves, more faint light was found than expected. This revealed that the universe was denser in earlier times. The static state theory failed. Another attempt was that the universe was first contracting, then slightly rotating, or due to some rotation or disturbance, it did not gather all together and began to expand again. Scientists in the Soviet Union developed this theory, which was part of the communist ideology. It was absolutely correct because it didn't require God. I began my research when the Russians argued that the universe had no beginning. I found this question very important, but their reasoning didn't hold true. We usually think that every event is connected to a previous event. But if we assume there was an event at the beginning, how did it happen? Most scientists avoided such questions. Some said the universe never had a beginning. Others said this was a question of metaphysics or religion, not science. But I believe that if the rules of science don't apply to the beginning of the universe, then when will they apply? Rules should apply all the time, not just sometimes. We should try to understand the beginning of the universe through science. Roger Penrose and I proved using the mass formula that if Einstein's theory is correct, then the universe definitely had a beginning. In the end, even the Russian scientists accepted that the universe had a beginning. However, our theorem only showed that there was a beginning, but not how. In the beginning, everything was confined to a single point, called a singularity, where Einstein's theory ceased to function. Therefore, science couldn't answer beyond that point. A few months after my research in 1965, a faint microwave background was detected everywhere in space. These are the same waves as in your microwave oven, but much weaker. If you heat a pizza with them, it will reach 270 degrees, meaning it will freeze. The white and black snow seen on empty channels in old analog TVs was partly due to these microwaves. This suggests that the universe was once very hot and dense, and as it expanded, these waves cooled. But the idea of a singularity didn't appeal to me and many others. The reason is that Einstein's theory of general relativity is a classical theory. It assumes that the position and speed of every particle can always be determined. However, in the early 20th century, scientists realized that this wasn't possible at very small scales. There's a kind of uncertainty in nature that can't be eliminated, no matter how good the theory. This is called the uncertainty principle, formulated by Werner Hagenberg in 1927. You can never know position and speed exactly at the same time. The better the position, the less speed, and vice versa. Einstein didn't like the idea that the universe operates by luck or chance. He said God doesn't play dice, but all the evidence so far suggests that the universe is like a gambling den, a casino, where dice are being rolled all the time. Just as in a casino, the result of repeated rolls of dice, on average, favors the winner. Similarly, in the universe, the outcome can be predicted if there are a very large number of things. But the universe was very small, like at the time of the Big Bang. So every roll matters a lot here. This uncertainty principle plays the most important role. This is why, to understand the beginning of the universe, we had to combine the uncertainty principle with Einstein's theory. This has been the biggest challenge in theoretical physics for the past 30 years. While it hasn't been fully resolved, significant progress has been made. Now, if we try to predict the future, because we can't fully know the position and speed of a particle at the same time, we can only derive probabilities for what will happen next. This means that the future of the universe has many possibilities. Similarly, we can understand the past in the same way. Based on what we can observe, we can only assign probabilities to different histories of the universe. This means that the universe has many possible histories. Each one has its own chance. For example, there's a history in which England wins the World Cup again, even though its probability is low. This sounds like science fiction, but now it's science fact. This idea was proposed by Richard Feynman. Feynman's method assigns a probability to every possible history and then uses it to predict the future. This method has proven to be very accurate, so it is believed to work for the past as well. Scientists are now trying to combine Einstein's theory and Feynman's idea of multiple histories to create a unified theory that can explain everything that happens in the universe. However, this theory won't explain how the universe began. For this, we need boundary conditions that describe what happens at the edges of the universe. However, if the boundary is a simple point, we can move beyond it. If the boundary is very jagged, it becomes difficult to understand the rules there. Therefore, it's not clear which boundary condition to choose. But Jim Hurtle and I thought that perhaps the universe has no boundaries at all, neither in space nor in time. Initially, this seemed different from the old mass theorem, but Feynman's mace uses the concept of imaginary time. We thought that the universe should have no boundaries in imaginary time. This is called the no-boundary proposal. If the boundary condition for the universe is that there are no boundaries in imaginary time, then there won't be just one history. There will be many histories. There will be many histories, and each one will determine a history in real time. So, many possible histories are created in the universe. Now the question is, why was the history we are living in chosen from all the others? There will be many possible histories in which the galaxy exists. Sea and stars would not form. Whereas this was necessary for us. It is possible that intelligent life could form without galaxies or stars, but the chances are very low. So even our being able to ask this question tells us that we are in one of those selected histories where there are galaxies and stars. This is called the anthropic principle. The universe must be as we see it, otherwise there would be no observer. Many scientists dislike the anthropic principle because it seems to have little predictive power. But it is essential, especially in understanding the beginning of the universe. M-theory, the most advanced theory right now, assumes many histories of the universe. Most of these histories are such that intelligent life cannot form. But according to Feynman, these could also be useless histories. In reality, we are only interested in those histories where intelligent life forms, whether human or otherwise. Even intelligent behavior in humans has not always been good. Take one example. We live in 3 dimensions. In 3 dimensions, why? Why isn't space 2, 4, or more dimensions? M3 has 10 space dimensions. 7 of them are so small they're invisible, and 3 are large. Like the surface of a straw, it's 2 dimensions, but one direction is very small. If there were only 2 dimensions, intelligent life would be difficult. In 3 dimensions, planets can revolve stably around their suns. If there were 4 dimensions, planets' orbits wouldn't be stable, and atoms wouldn't even survive. This means that 3 dimensions are special for life like ours. Another special feature in the universe is the microwave background. It's like a very old photograph of the universe. It has very small differences in every direction. The explanation for this is believed to be a very rapid inflationary expansion at the beginning of the universe. But where did these small irregularities come from? In 1982, I proposed that they arise from quantum fluctuations, which occur due to the uncertainty principle. These tiny differences formed galaxies, stars, and ultimately, us. This idea was later proven correct, as the COBE satellite discovered these differences in 1993. In 2003, the WMAP satellite created a high-quality map of the universe. The irregularities visible in it are the very factors that formed galaxies and stars. We are all products of quantum fluctuations. This means God truly plays dice. Now, the Planck satellite is observing the universe in even better detail and may even find traces of gravitational waves, further strengthening the theory. It's possible that there are more universes. According to M-theory, many universes must have been created, and each universe has multiple histories and multiple states. Most will not be like ours. Perhaps in the future, evidence for M-theory will be found at CERN's Large Hadron Collider, LHC particle accelerator. In 2012, the LHC discovered Hughes particles, the first new discovery of the 21st century. The beginning of the universe, the hot Big Bang, is the largest high-energy laboratory where our theories are tested. Different theories leave their own imprints on the structure of the universe. There may be other universes, but we will probably never see them. Now, 2 big questions remain. Will the universe end? Is it unique? The future of the universe depends on the amount of matter in it. If there is too much matter, gravity will bring galaxies together and crush them all together. This is called the Big Crunch. If there is too little matter, the universe will continue to expand, gradually cooling and becoming empty. Either way, billions of years are still left. I tried to explain how the universe began. What is its future and what is its nature? The universe was initially very small and dense, but it contained everything. Hamlet was right. We can be kings of infinite space even while confined within a small shell. What existed before the Big Bang? According to the no-boundary proposition, this question itself is meaningless. Like what is further south than the South Pole? The concept of time doesn't exist outside the universe. Therefore, before the Big Bang, there was nothing. Time itself began here. Chapter 3. Is there other intelligent life in the universe? I wonder how life began in the universe, and especially how intelligent life came to be. This includes humans, even though their behavior is often unintelligent. I have 2 questions. Is there life elsewhere in the universe, and how can life develop further? We've all seen that over time, things become more scattered, disordered, and chaotic. This is the second law of thermodynamics. That is, the total disorder of the universe is always increasing. But this law applies only to total entropy. Order can increase within a single object if the entropy around it increases further. This is what happens to any living being. Life in any living thing can be understood as a system that sustains itself and can reproduce itself. This requires converting energy from an ordered form, such as food, sunlight, or electricity, into something unordered, such as heat. This is how the system maintains order in itself and its next generation, or offspring, but it increases entropy outside. It's a bit like how every time mom and dad bring home a new baby, chaos or entropy occurs. A living system has 2 parts. An instruction set that tells itself how to operate. It has to be run and expanded. Like genes and a mechanism that follows these instructions, like metabolism. However, it doesn't have to be just biological. For example, a computer virus can also make copies of itself, so it can also be considered life under this definition. The life that humans have created so far is completely destructive. Computer viruses, and perhaps even these created computer viruses, reflect our nature. Generally, life is based on carbon chains. Life can be imagined from other chemicals like silicon. But carbon is the most advanced because its chemistry is the richest. Atoms like carbon could only be formed when nature's physical constants are very finely tuned. If these values were different, carbon atoms would not survive. The universe seems to be very well set, as if it were made for humans. But this is also because if the universe were not perfect, we would not exist. This is called the anthropic principle. The strong anthropic principle states that there are probably multiple universes. Everyone's value is different, and we are in the one that allows life to form. The weak anthropic principle states that we should only look at the value found to determine how life came about. At the time of the Big Bang, there was no carbon in the universe. Everything was just particles of protons and neutrons. As the universe cooled, some neutrons and protons combined to form helium. This prevented heavier elements like carbon and oxygen from forming initially. Everything was so hot that molecules could not form. Gradually, the universe cooled, and as more matter accumulated in certain places, galaxies and stars formed. Large stars burn hydrogen and helium internally to form heavier elements like carbon, oxygen, and iron. Later, these stars explode as supernovae, spewing out the outer elements into space, giving rise to new generations of stars and planets. There are two ways to find planets around other stars. If a star's light dims slightly every now and then, a planet may be passing in front of it. Another method is to look for slight shifts in the star's position, which could be caused by a planet orbiting it. Thousands of such planets have been discovered to date. It's estimated that 1 in 5 stars could have an Earth-like planet. Our solar system formed about 4.5 billion years ago when gas from the fragments of old stars accumulated. Earth is also made of heavy elements including carbon and oxygen. Some of these atoms were arranged in molecules similar to DNA. DNA forms a 2-chain double helix consisting of 4 types of nitrogen bases: adenine, cytosine, guanine, and thymine. DNA makes copies of itself, and its bases are used to make proteins and other chemicals. We still don't know how DNA first formed because it's very difficult to form DNA randomly. Some believe that life came from elsewhere, such as Mars, on a rock. However, DNA doesn't survive long in space radiation. If life were extremely difficult to form on a planet, it would take a long time. But life appeared on Earth very quickly, about 3 billion years ago when Earth was only 500 million years old. This suggests that life could have formed spontaneously if the right conditions were met. Perhaps DNA had a simpler organization before, such as RNA. RNA is simpler than DNA and can make copies of itself in short lengths. To date, we haven't created DNA or RNA from non-living material in a lab. But given 500 million years and an entire ocean, it might be possible. Random mistakes occur during DNA copying. Most are useless and die out. Some remain normal, and some special mistakes are beneficial for the species. This is natural selection. Initially, biological evolution was very slow. It took 2.5 billion years for simple cells to evolve into multicellular organisms. After that, some cells evolved into fish, then some fish into mammals, and then humans. Humans only took 100 million years to develop because the essential parts were already formed. Only fine-tuning remained. The biggest change in evolution came with humans, language, especially writing. This allowed knowledge to be passed from one generation to another, beyond DNA. DNA has undergone only a few changes in the last 10,000 years, but knowledge has increased significantly. I have written books to share my learnings with you so that my knowledge can be shared with you. The DNA in a human egg or sperm contains approximately 3 billion base pairs. However, most of this information is useless or inactive. In reality, the useful information in our genes is only about 100 million bits. 1 bit represents a yes or no answer. For comparison, a novel contains approximately 2 million bits of information. This means that one human is equivalent to approximately 50 Harry Potter books, and a large library could hold 10 trillion bits of information. The information available from books or the internet is 1,000,000 times more than DNA. The most important thing is that information in books or the internet can be changed or updated very quickly. Human DNA changes only a few million bits over millions of years, meaning 1 bit per year. However, 5,000 new books are published in English every year, containing billions of bits of new information. Most of this is useless. Yet, new information is being added at a rate millions of times faster than DNA. This means we are now in a new phase of evolution. Previously, evolution occurred through Darwinian natural selection, random mutations from mutation. This Darwinian phase lasted 3 billion years and led to humans, who developed language. But for the last 10,000 years, we've been in the external transmission phase, where knowledge, in addition to genes, is also passed on through books and other materials. Some people believe that it should be attributed solely to genes. But I believe that humans are not just our genes. We may be similar to our caveman ancestors in power or intelligence. But the only difference is the knowledge we've accumulated over thousands of years. Therefore, external information should also be considered part of evolution. Previously, external evolution used to take hundreds of thousands of years to add new information. Now this time has decreased to less than 50 years. But our brains still operate on structures that are thousands of years old. That's why problems have arisen. It used to be said that a person could read all the books. Now, even if you read one book every day, the library wouldn't be finished because by then, more books would be printed. Now, no one can master all human knowledge. Everyone has to become an expert in their own field, and this could become a major limitation in the future. Such rapid growth of knowledge will no longer be possible, and the biggest danger is that humans still harbor the same old instincts, especially aggression. This was good for survival in the past, but now it can become a threat to humanity itself, like nuclear war, genetic viruses, or the greenhouse effect. Now is not the time to wait for Darwinian evolution to automatically make humans smarter or better. We are moving towards self-designed evolution, where we can change our own DNA. Now that we have mapped DNA, we can also improve it. Initially, these changes will be solely for curing diseases, such as cystic fibrosis or muscular dystrophy. But other traits, such as intelligence, are difficult to find. Nevertheless, in this century, humans will learn to change their own DNA. Perhaps laws will be enacted to prevent genetic engineering. But some will certainly try to do things like improve memory, disease resistance, or extend lifespan. Once such superhumans are created, others will be unable to compete with them. In the long run, only those who can improve themselves will survive. If humans can design themselves and survive, they could eventually colonize planets and stars. However, such long-term space travel would be extremely difficult for DNA-based life, as our natural lifespan is very short. We can't travel faster than the speed of light, and it would take 8 years to reach the nearest star. It would take 500 years to reach the center of the galaxy. In science fiction, people travel through spaceships or extra dimensions, but this isn't possible in the real world. Otherwise, we would already be seeing tourists from the future. Perhaps genetic engineering could keep DNA life alive for a very long time. But the easier way is to send machines. Machines can be made so strong that they can travel long distances in space. They could land on a new planet, create new machines, and then send them further. These machines will be a new life form based on mechanical and electronic components. Perhaps in the future, these machines will completely replace DNA life. Will we find alien life as we explore the galaxy? If life develops so quickly on Earth, there must be life around other stars as well. Some planets may have formed even earlier than Earth. So why isn't intelligent machine or biological life visible in the galaxy? Because no aliens have visited or occupied Earth. By the way, I don't believe UFOs are alien ships. If aliens ever came, everyone would know. It probably wouldn't be good. So why haven't aliens come? Perhaps life is so difficult to develop that Earth is the only planet with life. Or life developed in many places, but most of it didn't become intelligent. Intelligence isn't necessary for evolution. It's also possible that intelligence developed in very few places. Intelligence may not have any long-term benefits. Simple life forms like bacteria can survive even if all life is wiped out. Perhaps the creation of intelligence on Earth was also very difficult, as it took 2.5 billion years for a single cell to evolve into a human. This means that life may exist on other planets, but with much less intelligence. Another reason could be that after life forms on a planet, an asteroid or comet strikes, wiping out all life. Dinosaurs on Earth were wiped out in a similar way. Perhaps life on other planets simply didn't have that long a chance. A third reason could be that intelligent life itself destroys itself. This is a very pessimistic, very disappointing statement, but it could happen. I think the fourth reason is correct. Perhaps other intelligent life is somewhere far away, but has so far eluded us. In 2015, I launched the Breakthrough Listen program, which uses radio telescopes to search for extraterrestrial intelligent life. This is the largest scientific research program ever, involving thousands of hours of radio telescope time. Breakthrough Message is a competition in which humans can create messages that an advanced civilization can read. But we should refrain from responding until we ourselves have progressed a little further, because if we encounter a very advanced civilization, they might not like us very much. Just as the first people of America were delighted to meet Columbus, it didn't. If intelligent life exists elsewhere, would it be like us or completely different? Is there intelligent life on Earth itself? But if intelligent life truly exists, it must be far away from us. Otherwise, it would have arrived on Earth by now, and if it had, we would have known it, just as in the movie Independence Day. Chapter 4. Can we predict the future? In ancient times, people believed that everything in the world happened suddenly and without reason. For example, floods, diseases, earthquakes, or volcanoes suddenly appeared. At that time, people believed that these things were caused by various gods. No one knew what would happen next. Therefore, people would do anything to please God so that their wishes would be fulfilled. Even today, many people think the same way. For example, if I get an A or pass a driving test, I will become a good person. Gradually, people noticed some regularity in nature's behavior. People first noticed how the sun, moon, and stars move in the sky, and this marked the beginning of astronomy. Newton formulated the law of gravity 300 years ago, and even today, we understand the movements of almost all celestial objects through it. Gradually, it was discovered that other natural phenomena also operate according to their own scientific laws. This gave rise to the idea of scientific determinism. The French scientist Laplace argued that if we knew the position and speed of all the particles in the universe at any given time, we could calculate their future or past. Someone asked Laplace what God was needed for this theory. He replied, "I don't need God in this theory." Laplace wasn't saying that God doesn't exist, but simply that God doesn't break the laws of science. If a law doesn't always apply, then it's not a law at all. Laplace's thinking was that if the state of the universe is known at any given time, then its state at all times can be predicted. This means that the future can be predicted, at least in theory. But in reality, it's very difficult, because the equations are very complicated and often involve chaos. For example, something as small as a butterfly flapping its wings in Australia could cause rain in New York. But this won't always happen. This is why weather forecasts are often inaccurate. Despite these difficulties, determinism was the official thinking until the 19th century. However, two developments emerged in the 20th century that thwarted Laplace's vision of future prediction. The first was quantum mechanics, introduced by the German physicist Max Planck in 1900. According to the classical idea, any hot object would emit all kinds of radiation. But if that were true, everything would be equally hot, which is not true. Planck argued that energy always comes in tiny packets, or quanta. For example, sugar is always available in packets, not loosely packed. The energy of each quanta is fixed. The higher the frequency, the more energy. This is why we don't get sunburn from a coffee cup. Initially, even Planck didn't believe it was quantal. But gradually it was discovered that the behavior of particles is also discrete. That is, it changes in small units, not absolute values. For example, the spin of a particle is in fixed units, not any value. After some time, people realized that this quantum behavior affects determinism. In 1927, Werner Heisenberg explained that you can never measure both the position and speed of a particle exactly at the same time. To measure the position, you need to shine light. But the shorter the wavelength of light, the more the particle's speed changes. This means that the more accurately you measure one thing, the more inaccurate the other becomes. This is called the uncertainty principle. Laplace's determinism meant that if you know the position and speed of all particles, you can also predict the future. But Heisenberg's uncertainty principle changed this thinking. If you don't have accurate data, your calculations can't be correct. Einstein disliked this kind of randomness in nature. He said, God doesn't play dice. He believed that uncertainty existed only for the time being. In reality, everything is fixed, which perhaps God knows, but we don't. But British physicist John Bell proved through experiments that the hidden variable theory was wrong. This meant that even God was bound by the uncertainty principle. Everything in nature happens according to chance and dice. Other scientists quickly abandoned classical determinism and turned to quantum mechanics. According to quantum mechanics, the position and speed of particles are not fixed. They have a wave function. The wave function describes the probability of finding a particle at any given location. If the wave function is very strong at some place, the uncertainty of position will be less, but that of speed will be more. If the uncertainty of speed is less, then that of position will be more. Everything is hidden in the wave function itself. From it, you can derive the probability of the future. This is a new version of determinism, in which everything is not absolutely fixed. But going beyond quantum mechanics, when it comes to black holes, even more problems arise, because there are some places where we can never see anything. So, overall, the classical thinking was that the future can be completely predicted. Heisenberg's theory showed that this is not the case. Only some things can be predicted accurately, and for things like black holes, even that is probably not possible. Do the laws of the universe give us such a clear idea? Do they allow for accurate predictions? The short answer is no. And yes, laws allow us to predict the future in theory, but in reality, calculations are very difficult. Chapter 5. What is inside a black hole? Black holes in real life are so strange that even science fiction pales in comparison. This is not a story, but real science. The idea of a black hole was first proposed in 1783 by John Michell of Cambridge. He argued that if an object is thrown upward so fast that its speed exceeds the escape velocity, gravity will not be able to bring it back. The Earth's escape velocity is 11 kilometers, the Sun's is 67 kilometers, and the speed of light is 300,000 kilometers. But if there is a star whose escape velocity exceeds light, even light cannot escape from it. Such stars were called dark stars, which are now known as black holes. To understand black holes, it's essential to understand gravity. According to Einstein's general theory of relativity, gravity, space, and time are all interconnected. Gravity is much weaker than other forces, but it's unique for two reasons. First, it exerts its influence over very long distances. And second, it's always attractive. If a star is very massive, its gravity can become so strong that it pulls itself inward and collapses. It took a long time for scientists to understand that massive stars could collapse into themselves due to their own gravity. Even Einstein himself thought this was impossible. But later, American scientist John Wheeler suggested that this was the future of many stars. Gradually, as stars run out of fuel, they shrink. Some may become white dwarfs or neutron stars, but Chandrasekhar explained that if a star's mass exceeds 1.4 suns, it collapses in on itself and becomes a black hole. In 1939, Oppenheimer explained that when very massive stars run out of fuel, even pressure cannot save them, and they form a singularity at a certain point. This means that space and time end there. This is where all our scientific theories fail. A few years later, quadrilaterals were discovered, which, despite being very distant, appeared extremely bright. The answer was gravitational collapse. Energy is released due to gravitational collapse. When a star collapses, it pulls in everything around it. Roger Penrose proved that no matter how irregular the star is, if gravity is attractive, a singularity is certain to form. But according to cosmic censorship, this singularity always remains hidden within the black hole, invisible to the outside. A black hole is a place where gravity is so strong that even light cannot escape. A black hole has a border called the event horizon, beyond which even light cannot escape. It's like falling from a boat into a waterfall. Once you cross the edge, it's impossible to get back. If it's a small black hole, a person would be sucked in like a spaghetti strap. This won't happen with a large black hole. You'll fall straight across the event horizon. If you're falling into a black hole, you won't notice much difference. But to an outside observer, you'll gradually appear slower, and eventually disappear. To the outside world, you'll be lost forever. For me, the most significant discovery about black holes was the area theorem. It states that if something falls into a black hole, the area of its event horizon always increases. If two black holes collide and merge, the area of the new black hole's event horizon will be greater than the total of the two previous ones. This has also been tested with the Thorium Laser Interferometer Gravitational Wave Observatory, LIGO. There is a strong relationship between the area of a black hole's event horizon and its entropy. Entropy is a measure of the disorder or unknown state of any system. According to the laws of thermodynamics, entropy always increases. Similarly, the area of a black hole also increases. The final state of a black hole is determined by three things: mass, angular momentum, and electric charge. How the black hole was formed doesn't matter. Only these three parameters of a black hole matter. This suggests that any black hole could form in countless ways. Quantum mechanics has the uncertainty principle, meaning you can't know the position and speed of any object with absolute certainty at the same time. This implies that any object has a minimum size that depends on its mass. If an object is very light, its wavelength will be large and it will appear diffuse. The heavier it is, the smaller its size. All this means that a black hole can only form in as many ways as its mass, angular momentum, and charge allow, and this number is finite. The entropy of a black hole, or the hidden information within it, is derived from this finite number. When a black hole forms, a significant amount of information is lost forever. If the area of a black hole is finite, then its entropy will be, and accordingly, its temperature must be. This means that a black hole can exist in equilibrium with thermal radiation at some temperature. However, classical science says this is not possible because the energy or heat that enters a black hole cannot be returned. This has become a major paradox. One theory was that identical black holes could form from countless different stars. Another theory says that this number is finite. It could be. It's actually an information problem. Information is hidden in every object and force. As John Wheeler said, if you look at a black hole from the outside, you only see its mass, charge, and rotation. What's inside? All that information is hidden, but only a limited amount of information can fit into any space, because information requires energy, and energy has mass. EMC2. Add more information, and that space will turn into a black hole. If the information hidden inside a black hole depends on its area, then by basic logic, the black hole should also have a temperature and glow like any hot object. But everyone thought that if nothing can come out of a black hole, it can't emit heat either. This problem persisted until 1974. Then, using quantum mechanics, I considered how matter would behave near a black hole. I was very surprised when I discovered that particles were being emitted from it. At first, I didn't believe it either, but the more I understood, the more this result persisted. Eventually, I accepted that a black hole, like any other hot body, emits particles and radiation, and its temperature depends on its surface gravity and is inversely proportional to its mass. This also proved Jacob Bekenstein's point that the entropy of a black hole is finite because its temperature is not zero. Now, many mathematical proofs have been found that black holes emit thermal radiation. One way to understand this is that, according to quantum mechanics, pairs of virtual particles are formed and annihilated everywhere. Near a black hole, sometimes one of these pairs falls in while the other escapes. This escaping radiation is visible as Hawking radiation. Another way is to consider that the particle that went in is traveling backward in time. The smaller the mass of the black hole, the faster it emits radiation. Small, mountain-sized black holes can emit X-rays and gamma rays. However, such black holes have not yet been discovered. Attempts have been made to create smaller black holes in particle colliders so that they can be observed directly, but so far, success has not been achieved. As particles escape from a black hole, their mass decreases and they eventually disappear. The question is, what happens to whatever falls into the black hole? The particles that escape are completely random, having no connection with the matter that went in. In this situation, all information is lost, leaving only mass, charge, and radiation. If information is truly lost, then one of the most fundamental principles of science, determinism, would be broken. This means that we will not be able to predict the future, or even the past could be a deception. Therefore, it is crucial to understand whether information is truly lost in a black hole or is stored somewhere. This problem, known as the information paradox, remains unsolved. Recent research has shown that black holes possess an infinite number of supertranslations, symmetries, and charges, which can reveal even more about the black hole from the outside. These charges have been called the black hole's hair. This means that black holes aren't as simple as they seem. There's a lot hidden within them. It's possible that all the information that enters the black hole is retained somewhere. From the outside, you only see mass, charge, and spin, but the rest of the hidden information may be stored at the event horizon. Research is still ongoing on this, but I think we're on the right track. If a space traveler falls into a black hole, it's very bad news for them. If the black hole is small, they'll be sucked into it like spaghetti. If it's a very large, supermassive black hole, you'll easily cross the event horizon. But eventually, reaching a singularity, they will be completely destroyed. Music, Chapter 6. Time travel is possible. Time travel and space-time are commonplace in science fiction. But is time travel possible in real science? Space and time can also bend. This idea is new. Previously, everyone thought that all three corners of a triangle would always be 180 degrees. But this isn't the case on a round surface like the Earth. If you draw a triangle on Earth, all three angles could be 270 degrees. This means that space isn't flat, but can also be curved. We live in 3 dimensions, but space could also exist in another dimension if space were round. So, no matter how many layers of paint you apply, space will end after a certain limit. Similarly, we can only determine the shape of our space through experiment. There are no fixed rules. This was all just mathematics until Einstein proposed the general theory of relativity in 1915. In this, not only space but also time can be curved. Einstein explained in 195 that both space and time are connected, and together they are called space-time. 4 numbers are required for every space, 3 for space and 1 for time. If 2 people move at different speeds, the time for both will be different. The higher the speed, the greater the difference in time. If someone travels faster than light, time can go backwards for them. But in reality, nothing can travel faster than light because that would require infinite energy. According to Einstein's theory, time travel seemed impossible, and space travel would also be very slow. If one traveled at the speed of light, it would take thousands of years to orbit a star. Science fiction found a solution to this problem: wormholes. Shortcuts in space-time that allow quick travel from one galaxy to another. In 1915, Einstein demonstrated that matter and energy can warp space-time, and we can see this with our own eyes, like the slight bending of light passing near the sun. This is often very slight, but measurable. Gravity around us is very weak, so space-time warps very little. However, in events like black holes or the Big Bang, gravity can become very strong. Some theories suggest that if space-time warps significantly, time travel, wormholes, and hyperspace could become possible. In 1948, Kurt Gödel derived a universe from Einstein's equations in which time travel was possible. But that universe was not like ours. Later, more possibilities were discovered, such as string theory, where cosmic strings are highly tense and can bend space-time in strange ways. In fact, time travel was possible in these universes from the very beginning. But our universe didn't start like that. The question is, can we later bend space-time enough to make time travel possible? This is an interesting topic for research, but also a very controversial one. If we can't go faster than light, wormholes could be a shortcut. But creating wormholes requires negative mass and negative energy, which are the opposite of normal matter. Previously, scientists believed that energy could always be positive. However, quantum theory suggests that negative energy is possible in certain places. This means that time travel isn't completely impossible. But as of now, it seems possible only in theory and science fiction. Science has only revealed that time travel requires a very strange type of physics and matter, which we don't yet possess. In quantum theory, energy density can be negative because the uncertainty principle applies. This means that both the position and speed of a particle cannot be determined with absolute precision simultaneously. The more the position is confirmed, the greater the uncertainty of the speed, and vice versa. The same applies to electromagnetic or gravitational fields. These fields can never be zero, otherwise the uncertainty principle would be violated. This is why, even if space appears empty, there will always be some minimal fluctuations. These are called vacuum fluctuations or virtual particles, which suddenly form, separate, and then merge and disappear. These virtual particles cannot be detected directly, but their effects can be observed. For example, the Cassirer effect, in which there are fewer virtual particles between two metal plates. This reduces the pressure between the plates, causing them to pull together. This force has been measured experimentally. This means that virtual particles actually exist and exert an effect. Because there are fewer virtual particles between the plates, the energy density there is negative compared to the outside. However, to keep space flat, the energy outside remains zero. Therefore, a negative energy density is obtained between the plates. This proves that space-time can indeed be curved, and even in the negative direction. So it seems that if science and technology advance, perhaps we will be able to bend space-time for wormholes or time travel. But if so, the question arises: if time travel is possible in the future, why hasn't anyone come from the future to tell us? Even if there were a reason for not telling us, it's still hard to believe that no one would. Some people say that UFOs come from the future, and governments are hiding it. But I don't believe such things. If aliens or future travelers really did come, we would have concrete proof of it by now. Another way to understand that time travel is only possible in the future. This means that the space-time of the past is fixed, but the future is open, where we could perhaps move space-time enough to allow time travel. But if that were true, we could never return to the past or the present. We could only travel to the future. Even if that were true, many problems would remain. Suppose someone traveled in a rocket and blew up their own rocket before returning. How did they travel? There are many such time travel paradoxes. For example, a time traveler might kill their parents before they were born. This can be answered in two ways. The first is the consistent histories approach. In this, all the equations of physics would be formulated in such a way that no time traveler could change their own past. This means there is no room for freewheeling. Everything is predetermined. The second is the alternative histories approach, proposed by physicist David Deuce. In this approach, every time a time traveler travels to the past, a new universe or history is created. This means that a rocket is launched in one history. In the second, the time traveler returns and stops the rocket. David Dush says this is similar to the sum over history's idea of quantum theory, which includes every possible history of the universe. But in reality, the histories of physics are complete and consistent, and the time traveler will remain in only one history. He will not create any new ones, so it seems that only consistent histories will remain. But practically, the probability of histories in which time travel is possible is very low. This is called the chronology protection conjecture. The universe itself prevents time travel. It prevents this so that historians' jobs remain safe. Whenever space-time becomes so warped that time travel becomes possible, the number of virtual particles and their energy increases significantly, further reducing the probability of such histories. This is perhaps why time travel cannot occur on a large scale. Now, the M-theory version of string theory suggests that space-time should have 11 dimensions, 7 small and 4 large. If this is true, then perhaps we will be able to do something in the future that we cannot even imagine now. Overall, according to today's science, fast space travel or going to the past is not impossible, but it is very difficult and fraught with logical problems. Perhaps the universe itself has banned time travel, but science fiction fans can remain hopeful. Perhaps a new way will emerge in the future. In 2009, I hosted a party for time travelers and sent the invitations after the party so that only real time travelers could attend. That day I sat in college, but no one came. I was a little disappointed but not surprised, because science says time travel isn't possible. If someone had, it would have been fun. From the chapter, Will We Survive on Earth? In January 2018, a scientific general set the doomsday clock 2 minutes ahead. This means the world could be in danger at any time, whether for military or environmental reasons. This clock was started in 1947 when the atomic bomb was newly invented. At that time, scientists felt the world had changed a lot, and even then there was a fear that everything could end. Now this clock is back to the same danger it was during the Cold War. This clock is just a symbolic warning, but we should take it seriously. I personally understand the value of time because at a very young age, doctors told me I only had a few years left. Yet, I lived to be 76. I have always been alert and thankful about time. The world today is more politically unstable than ever before. Many people feel left behind. Therefore, they are electing politicians with little experience in running a government. This increases the chances of mistakes and the risk of a doomsday clock. The Earth faces so many threats that it becomes difficult to think positively. First of all, the Earth is becoming smaller. Our resources are depleting rapidly. We have created problems like climate change, rising temperatures, melting ice, deforestation, overpopulation, disease, war, famine, water scarcity, and the extinction of animal species. All these problems can be solved, but they haven't been. Global warming is happening because we all want a good lifestyle, cars, and travel. But by the time people realize this, it may be too late. Now, the dangers of both nuclear war and climate change are looming large. It is the duty of scientists to alert people and leaders to the dangers and provide sound advice. If governments and society don't take action now, the damage could be enormous. On the other hand, many politicians either don't believe in climate change or believe that humans can't change it. This poses the greatest threat because if global warming accelerates on its own, such as when ice melts, reducing reflection, or forests disappear, temperatures will rise even further. The climate could deteriorate so much that Earth becomes like Venus, with temperatures reaching 250 degrees Celsius and acid rain. In that case, human life would become impossible. We must reduce carbon emissions now. We have the technology. We just need political will. The universe itself is very dangerous. Stars can swallow planets. Supernovas emit dangerous rays. Black holes collide. Asteroids rotate rapidly. This doesn't mean space is safe. But this is precisely why we must leave Earth. The last time an asteroid hit Earth, the dinosaurs were wiped out. Physics and probability suggest that it will happen again, and we cannot escape it. Nuclear war remains the greatest threat today, a threat we may have forgotten. If a nuclear weapon were to accidentally or fall into the hands of terrorists, everything could be destroyed. Today, there are so many weapons that humanity could be wiped out many times over. Even if the nuclear threat diminishes in the future, new threats could emerge. Therefore, we must always remain alert. I believe that in the next 1,000 years, either nuclear war or an environmental disaster will cause great damage to the Earth. But hopefully, by then, we humans will have learned to live somewhere outside the Earth. This will not be possible for other animals, and that is our responsibility. It is very difficult to say how science and technology will develop in the next 1,000 years. but I will try to make my own predictions, at least for the next 100 years. The rest is just speculation. The origins of modern science are almost as old as the arrival of Europeans in North America. By the 19th century, it seemed that we could understand the universe using classical laws. But in the 20th century, it was discovered that energy comes in tiny quantum states, and Max Planck and others developed quantum mechanics. In this theory, things have not just one, but many possible histories, each with its own probability. When we go down to the particle level, there are paths that travel faster than light, or go backwards in time. Even empty space is filled with particles that move through space and time. The problem is that space-time has infinite points. And there are also countless particle loops that can generate countless energies, which will compress space and time into a single point. Avoiding this requires very creative mathematics. A lot of work in theoretical physics is currently being done on how to make all these infinities cancel each other out so that quantum theory and general relativity can merge to form a complete theory of the universe's laws. Will we find this final theory in the next 1,000 years? I hope so, because I'm an optimist. In 1980, I said there was a 50-50 chance we would find this theory in the next 20 years. A lot of progress has been made, but the final answer still seems a little far away. At the beginning of the 20th century, we understood nature as much as classical physics could, down to 1/100ths of a millimeter. Then, atomic physics took us to millionths of a millimeter. Now, nuclear and high-energy physics have shown us scales billions of times smaller than that. But there's a limit like the smallest box in a Russian pail. In physics, this smallest length is called the Planck length, which is equal to 100th or so. DNA was formed 2.5 billion years ago and is the foundation of all life. DNA is a double helix consisting of 4 nitrogen bases: cytosine, guanine, adenine, and thymine. Their sequence contains all genetic information. When DNA copies itself, mistakes sometimes occur. These are called mutations. Most mutations are bad. However, sometimes a beneficial mutation makes life stronger. Such mutations gradually increase and life becomes more complex. This is called natural selection, as Charles Darwin explained. What is the biggest threat? The biggest threat is an asteroid impact. We currently have no way to avoid this. The last one occurred 66 million years ago, wiping out the dinosaurs. Perhaps the biggest threat right now is climate change. If ocean temperatures rise, the ice will melt, releasing a lot of carbon dioxide. Both of these could cause the Earth to resemble Venus, where the temperature is 250 degrees Celsius. Music, Chapter 8. Should we colonize space? Why should we go into space? Why spend so much money and effort? Many people will say that there are so many important things to do on Earth. So what's the point of space exploration? The simple answer is that space is all around us. And if we remain stuck on Earth, it would be like a human being stranded on an island with no attempt to escape. We should explore the solar system to find out where humans can live. It's just like the first Europeans did in 1492. People said sending Columbus was a waste of money. But the discovery of the New World changed everything. Similarly, if we expand into space, humanity's future could be completely transformed. It could even determine whether we survive. It won't solve our Earth's problems, but it will provide a new perspective, and perhaps even unite everyone. Going into space is a very long-term plan. A long-term strategy is a matter of hundreds or thousands of years. We can build a base on the moon in the next 30 years. We can reach Mars in 50 years, and we can go to the moons of the outer planets in 200 years. I'm talking about missions where humans will travel on their own. Robotic missions are already underway. Space exploration won't be cheap. But even if it costs a small portion of the world's total income, it will be possible. NASA's budget wasn't very large even before. Even if the global budget were increased 20-fold, it would still remain a small portion of total GDP. Some people would argue that money should be better spent on Earth's problems like climate change and pollution, rather than on the search for new worlds. I'm not saying that fighting climate change isn't necessary, but spending 1 or 4% of GDP on space isn't wrong. Even in 1960, we felt the need to go to space. President Kennedy gave America the target of sending humans to the moon. And in 1969, Neil Armstrong and Buzz Aldrin reached the moon on the Apollo mission. This energized both human thought and science. Many scientists entered science for this reason. But after 1972, when lunar missions ceased and no new plans were made, public interest waned. If we restart a major human space program, enthusiasm could be revived among the younger generation. Robotic missions are cheaper, but humans going into space themselves capture the public imagination more. My own dream was space travel, which I never seemed to achieve. But in 2007, I had the opportunity to experience weightlessness in a zero-gravity flight for just 4 minutes. But the experience was amazing. I've always believed that if we don't go into space, humanity's future is in danger, and I believe everyone can participate in space travel in some way. Can humans survive away from Earth for long periods of time? Experience with the International Space Station shows that humans can survive for a few months. However, zero gravity has adverse effects on the body. Weak bonus practical problems. Therefore, it's better to build a long-term base on a planet or the moon. There, you can go underground to protect yourself from thermal insulation, meteors, and radiation, and you can also obtain essential supplies from there. The best options for humans in the solar system are the moon and Mars. The moon is closer and easier to reach. However, there's neither air nor magnetic field nor water. Perhaps ice is found at the poles. Oxygen can be extracted from the ice, and solar panels or nuclear power can be used for energy. Mars is the next target. It receives half the sun's heat and previously had a magnetic field, which is now gone. Therefore, there is no protection from solar radiation. The air there is very thin today. It doesn't have even 1% of Earth's water, but it did in the past. Perhaps that's why life once existed there. If we find evidence of life there, it means that under the right conditions, life could exist elsewhere. But we shouldn't contaminate Mars with our own life, nor should we bring life from there to Earth. Otherwise, there are risks. NASA has sent numerous spacecraft to Mars since 1964, orbiters, rover, etc. The surface is desert-like and water can be extracted from the ice. There are also volcanoes there, which could yield minerals and metals. The Moon and Mars are the best candidates. Mercury and Venus are very hot. Jupiter and Saturn are gas giants. Some moons, such as Europa and Titan, may have potential. Water may exist beneath the ice on Europa. Titan has a thick atmosphere but is very cold. Looking outside the solar system, our observations have shown that most stars have planets. Some of them may be Earth-like, located in the Goldilocks zone, where water could exist. There are thousands of stars around us, and if 1% of them have such planets, we could discover 10 new worlds. For example, Proxima b is the nearest exoplanet, located near the star Proxima Centauri, and research suggests it may be somewhat Earth-like. Reaching new worlds is also impossible with today's technology. However, if we use our imagination and innovation, we can make interstellar travel a long-term goal in the next 200 to 500 years. Rocket speed depends on 2 factors: exhaust speed and how much mass is lost during flight. Currently, chemical rockets have an exhaust speed of about 3 kilometers per second. If a rocket jettisoned 30% of its mass, it could reach speeds of half a kilometer per second. NASA estimates that reaching Mars would take about 260 days. However, reaching the nearest star system would take 3 million years. To go faster than this, we need energy comparable to the speed of light. Nuclear fusion can use 1% of its mass and energy to accelerate to 1/10 of the speed of light. To go further, we need either matter-antimatter annihilation or a completely new energy source. The truth is, interstellar travel is simply impossible with current technology. Alpha Centauri will never become a holiday destination. But our imagination and brainpower can change all that. In 2016, I joined the Breakthrough Starshot project with entrepreneur Yuri Milner, which aims to make interstellar travel a reality. If successful, a probe could be sent to Alpha Centauri within our lifetimes. So far, our space exploration has been limited to the neighborhood. That Aegean spacecraft reached interstellar space in 40 years. Its speed is 11 miles per second, but it will take 7,000 years to reach Alpha Centauri. 70,000 years. Alpha Centauri is 437 light-years away. That's 25 trillion miles. We are now entering a new space age. Initially, private astronauts will be pioneers, and the first flights will be very expensive. But in the future, space travel will become accessible to many people. This will change our thinking and our responsibilities. We will understand our place on our planet and in the cosmos. Breakthrough. Starshot consists of 3 elements: mini spacecraft, light, propulsion, and phase-locked lasers. A star chip, a space probe a few centimeters across, will be connected to a light cell. These cells will be made of metamaterials and weigh only a few grams. Thousands of nanocrafts will be sent into orbit. A large array of lasers on Earth will combine to create a powerful light beam that will propel these cells into space. Music. In this new idea, nanocrafts will ride on light beams, just as Einstein dreamed of riding a light beam as a child. They may not reach the speed of light, but they can reach 1/5 of it, i.e. 100 million miles per hour. At this speed, they can reach Mars in less than an hour, Pluto in a few days, Venus in less than a week, and Alpha Centauri in 20 years. Once there, the nanocrafts can take photos, data, and important readings and send that data back to Earth via laser beams. The most important thing is that this project will be able to reach Earth-like planets like Progma b. It can also study them. Breakthrough Starshot also has side goals, such as exploring the solar system or tracking dangerous asteroids. German physicist Claudius Gross has suggested that this technology could someday be used to create biospheres on other worlds. However, there are many technical challenges. Focusing such a powerful laser in the right direction, protecting the nanocrafts from space dust and other obstacles, and returning the data safely to Earth after 20 years. But these are engineering problems, and engineers will somehow solve them. When this technology matures, space travel could become much easier and faster. This will no longer be human interstellar travel, as they cannot stop, but this will be the moment when human culture reaches interstellar level for the first time. And if it sends an image of a habitable planet, it could change the future of humanity. Finally, if a planet is discovered in Alpha Centauri and its image is captured by a camera traveling at 1/5 the speed of light, the effects of special relativity will be visible. This was Einstein's dream. Einstein's theory is the basis of this entire mission. It makes lasers, guidance, and data transmission possible. We are at a point where human populations could settle on other worlds. This could become science fact, not just science fiction. Humanity is a specialty of exploring new paths. If humanity is to survive for the next million years, we must advance into space. The era of civilian space travel is now dawning. This means I will probably be among the first to buy a ticket. I think in the next 100 years we will be able to travel anywhere in the solar system, perhaps except for the outer planets. But reaching the stars will take a little longer. I think we could reach the nearest stars in 500 years. It won't be like a star trip. While that uptick may not be achieved, new avenues will still open up for humanity. Chapter 9. Will artificial intelligence outsmart us? Intelligence is the most important thing about being human. Our entire civilization is a gift of the human brain. DNA transmits life's knowledge from one generation to the next. Over time, the brain has become so advanced that it has learned to think and reason that life forms can recognize themselves. We are made of stardust and today understand ourselves and our universe. I believe there's no real difference between the thinking ability of a mudworm and a computer. If evolution made humans smarter, then computers can also become more intelligent than humans. According to Moore's law, if computer speed and memory continue to double every 1.5 years, then within the next 100 years, computers could become smarter than humans. When artificial intelligence learns to improve itself, it will advance so rapidly that humans will be left behind. Therefore, it's crucial that we align AI's goals with those of humans. Many people believe that technologies like AI are merely science fiction, but this would be a mistake. It could become a real threat. AI has made tremendous progress in the past few years. Speech recognition, image classification, autonomous vehicles, machine translation, and question answering. As this technology is becoming more and more prevalent in our lives, funding and research into it are also increasing. AI can solve major problems like disease and poverty. Therefore, it is important to understand its benefits as well as its risks. If successful, AI will be the greatest human invention. But this could also be the end if we ignore the risks. AI can enhance our intelligence, but if it gets out of control, humans will be left behind. The fear is that AI will continue to advance on its own without human control. In the future, AI may develop its own intentions or will that may even differ from humans. Some believe that humans can control technology for a long time, but I'm not entirely sure. In the future, countries' militaries are considering developing autonomous weapons that can select and eliminate targets on their own. There's a danger that such weapons will become affordable and accessible to criminals and terrorists. We must stop this race now. In the medium term, AI can automate our jobs. It can bring prosperity and equality, but problems can also arise. In the long term, there's no physical law that prevents AI from becoming more advanced than humans. Irwin Good has said that superhuman intelligence can repeatedly upgrade itself, leading to a technological singularity. In such a scenario, AI could outsmart financial markets, surpass humans in invention, and perhaps even control them. Superintelligent AI could be the best or worst for humanity. The real danger isn't its being bad, but its being too intelligent. If AI's goals diverge from ours, it could cause problems. Just as no human is an enemy of ants, If they have to work on a project and there are ants nearby, they don't care. We shouldn't put humans in such a situation with AI. Computational power is increasing. Quantum computing is emerging, which will make AI even more powerful. Technologies like CRISPR have made DNA editing possible, which can cure diseases. But this too carries risks, and we must be prepared for them. Intelligence means change. Adjust to it. Humans have always adapted to changing situations. We must not fear peace, but take advantage of it. Therefore, it is essential that the next generation receive proper education in science and AI, and that we, together, create tools for the common good. We must move forward with wisdom. When humans created fire, they made mistakes many times. Then they invented the fire extinguisher. But with the technologies we now have, such as nuclear weapons, synthetic biology, strong AI, we must make the right decisions the first time. Our future is a race between technology and our wisdom. We must win wisely. People ask why we fear AI. Can't humans always unplug it? Someone asked a computer if God exists. The computer replied, God exists, and fused the plug. Chapter 10. How do we shape the future? Nearly 100 years ago, Einstein transformed our thinking. He proposed a new way of understanding space, time, energy, and matter. Even today, his predictions seem to be coming true, such as the discovery of gravitational waves in 2016. The most remarkable thing about Einstein was his imagination. He thought about things in a new way, and even what seemed impossible, he believed it to be true. Today, we have numerous scientific tools: particle accelerators, supercomputers, space, and telescopes. But the greatest power is our thinking power, our imagination. It allows us to go anywhere and imagine anything. Since childhood, I've loved to observe things in detail. Therefore, I learned to understand. Now my job is to understand the rules of the universe so that humans can control things. It's not easy, but it's a lot of fun. I've had the opportunity to work with the greatest scientists all my life, and I was very fortunate to live during this remarkable era of cosmology. Every mind has a spark within it, a spark to learn and understand. Often this spark comes from a good teacher. The same thing happened to me when my math teacher inspired me to ask questions and think creatively. Behind almost every successful person is a teacher. Nowadays, funding for science and education is declining, and experts are underestimated globally. But science and technology are essential for future generations, because they are everywhere in today's lives. In the future, we will have to solve huge problems: global warming, a growing population, space and resource shortages, disease, and the loss of oceans and forests. Along with this, there will be many innovations, such as mining on the moon, colonies on Mars, and treatments for new diseases. Some people believe that humanity is now at the pinnacle of evolution. I don't think so. We must keep moving forward and push our limits. We have two paths: discover new worlds through space exploration and utilize artificial intelligence effectively. AI is growing rapidly. Self-driving cars, digital assistants, and many other technologies have arrived. AI could either be the best thing for humanity or the biggest problem in the future. Therefore, it's important to be cautious, adopt the right methods, and handle it with good management. Technology has completely changed my life. Today I can speak and communicate with the world using a computer. This technology was originally designed for the disabled and is now available to everyone. In the future, things like brain interfaces will make communication even easier. The internet, mobile phones, satellites, and social networks have all completely transformed our lives. Much more is yet to come. It's crucial that children take an interest in science, study, and reach their full potential. The internet now connects everyone. It's like a giant brain. If we all just sit together, nothing is impossible. Everyone should be connected to science. Whether they become scientists or not, it's important to understand science. If everything remains confined to a small group, big problems won't be solved. We need to bring everyone together. I believe the world will change completely in the next 50 years. We'll learn more about the Big Bang, how life began, and perhaps even find other life forms in the universe. We shouldn't just be confined to our small planet, but explore the universe, solving Earth's problems along the way. I hope that in the future, humans will live on other planets. This is just the beginning. Life will spread throughout the universe for millions and billions of years to come. This is the only hope. And most importantly, we never know who will make the next big discovery or where it will come from. We need to inspire children so that the next Einstein can emerge from anywhere. So always look up at the sky, ask questions, think about why the universe exists, and never give up.